we present text-to-talking face. During this presentation, we will discuss the background and motivation, our approach to our model, and the various experiments we conducted. So generating talking head video from text is challenging and unexplored. A text-to-talking head model would allow very flexible talking head generation and the ability to generate new video from novel sequences. In prior research, various researchers have shown that you can generate face landmarks from audio as well as realistic talking head video from audio sequences. However, very little research shows whether it's possible to generate talking head video directly from text sequences. So for our project, using powerful text-to-speech models, including other existing models, we explore the possibility that we can generate talking head videos directly from text sequences. So this is our high-level architecture of the text-to-talking face interface. Our model takes input text sequences, generates audio from text-to-speech models, then generates face landmarks from audio to face landmark models, and finally, our system generates talking head videos from face landmarks.
For our text-to-speech model, we'll be using Tacotron 2 combined with WaveGlow. In the original Tacotron 2 paper, they combine a spectrogram prediction network, which is illustrated here, with a WaveNet architecture for converting the output of the spectrogram prediction network in order to obtain the final audio samples. The input of the spectrogram prediction network is just a sequence of text characters, which are embedded and fed to a sequence of convolutional layers and a bidirectional LSTM. The output of this is a sequence of embeddings, which is the same length as the input sequence of characters, and these will be fed to a decoder, whose ultimate output will be a MEL spectrogram. The decoder itself will output a sequence of frequency distributions, which when combined along the time axis, get as the MEL spectrogram. The MEL spectrogram is the features fed to the WaveGlow network, which is the second component of our text-to-speech model. WaveGlow is a non-autoregressive improvement to the originally autoregressive WaveNet network that was used in the original Tacotron 2 paper. Our first experiment involves training Tacotron 2 and WaveGlow on the LJ speech dataset. This is a training loss plot over 1,500 epochs of Tacotron 2. The red curve is validation loss and the blue curve is training loss. We do see some convergence as we approach near the end of training. Similarly, we can also take a look at the WaveGlow network's losses. Note that this is inverted so that larger values are considered better here. One interesting characteristic which we saw consistently throughout training our text-to-speech models was that regardless of the data domain, it was nearly impossible to overfit WaveGlow in the sense that we would never observe the training loss outperforming the validation loss. We've also included in this slide some example samples from our trained model.
Hello, Stanford University. I am a text-to-speech model. I am so excited to be a part of this presentation.
Oh, well, we're excited to have you too. Another experiment we did was, instead of using the LJ speech dataset, we wanted to see if we could overfit the Tacotron 2 WaveGlow combination model on my voice. So what I did is I took the first 400 example text samples from the LJ speech dataset, and I simply recorded myself speaking those samples into this microphone. So here we see that I am able to reach convergence on training, and overfitting does appear to be occurring right around the 800 mark, where the validation loss starts going back up, indicating that we are in the realm of memorizing the training dataset. So all looks as well as expected here. Similarly, for the WaveGlow losses, we are getting steady increase, and as I mentioned in the previous slide, we do not see the same type of overfitting behavior in these curves. These training curves, while they look good, do not result in a model that produces high-quality speech outputs. The next few slides will focus on some failure analysis that we did to explore the possible reasons for this behavior. First and foremost, data preparation. Things that increase the fidelity of the model include things like volume normalization, so making sure that all samples of your audio are in the same volume range. Hop lengths of 256, this is related to the stride that we take along the audio frame as we sample audio that we're going to be using and feeding ultimately as vectors to our model. We also had to trim the audio on either side to a threshold of 27 decibels. It's extremely important. You cannot have essentially any gaps at the beginning or end of your audio. Otherwise, the resultant model tends to just predict emptiness. This might be an artifact due to the fact that the decoder being used for Tacotron 2 is autoregressive, although we would have hoped that the location-sensitive attention mechanism would have been able to help overcome some of this. Something that became increasingly clear was that fine-tuning on this model is quite difficult, and we were not able to do it successfully. By fine-tuning specifically, I mean that taking the LJ speech model, which was producing high-quality audio samples, and then subsequently training that network on my voice's audio samples, so a different speaker identity. So on the top row, we see the Mel spectrogram and time domain audio waveform of me speaking a single example from the LJ speech dataset. And similarly, on the bottom row, we see the original LJ speech dataset example. This was a part of our exploration in trying to determine all the various things that can happen to the features when you shift from one speaker to another, and why fine-tuning may be difficult for these models. We do see things like speaker cadence, how often they take pauses in between their words, their pitch, how often they change the frequency of the words as they're speaking, and the changes in volume that the speaker uses as they speak the sequence. So let's hear the sequence spoken by my voice. And to dispose him by meditation and seclusion to return to an honest life. And we can hear the original LJ speech speaker.
And to dispose him by meditation and seclusion to return to an honest life.
So due to how different these two examples really are, it was less surprising for us to figure out. It really is difficult for a model trained on one specific speaker and cadence and volume changes to go to a completely different speaker. There was very little transferability between the two. Granted, the initial losses when doing the fine-tuning were lower than if we did it from scratch, but in the end, the model was not able to converge at all.
As previously shown, researchers such as Mendez et al. Shows the possibility that we can generate face landmarks from audio sequences. We feel that this architecture is key to generating realistic talking head videos from text sequences, so we explore the system. The architecture involves extracting Mel spectrogram features from audio sequences and processing those features through a 4-layer LSTM model. The ATFL model generates 68 2D landmarks that represent face landmarks. In our experiment, we utilize a pre-trained ATFL model from the grid audio visual sentence corpus and evaluate whether fine-tuning is possible and how this model will perform on novel sequences. So our fine-tuning result shows here that we're able to successfully generate realistic face landmarks from audio sequences. Our dataset involves only a 2-minute video of a male speaker and training on only 2 epochs. Next, we talk about our landmark to face model. We use a pix-to-pix scan model that uses an input image of face landmarks converted to a binary image, and then using an encoder-decoder model, we then generate an RGB image of a talking head. We conducted experiments on fine-tuning this pix-to-pix model using female speaker sequences as well as male speaker sequences. What we end up with is we're able to successfully generate realistic talking head videos directly from face landmarks. Using only a small amount of data, 2 minutes to 3 minutes of video, we achieve strong loss results and strong qualitative results as shown here. Next steps for our project include passing text through our text-to-speech model, our ATF model, and our LTF model to analyze the performance of our text-to-talking face interface. We plan to scale and pre-train our LTF model on a much larger data set and see how well generalization and quality improves. Finally, we plan to resolve text-to-speech issues and train our text-to-speech models on novel data sets.